So this is a short paper. Interestingly, it's written by an all-female team. They are very well-known mid-career female scientists. They're talking about the futures of climate modeling. They reflect on the current state of climate modeling and the future divergent paths that have been proposed for a step change that leverages different tools. So some people say we should go to kilometer scale because the IPCC class models are not serving the decisions very well. Some people say AI is going to do everything for us, a lot of efforts in AI forecasting and so on. Some people say it should be a combination and so on. We review the history of successful Earth system predictions across timescales, highlighting how multiple tools and steps were involved. We argue that the past is prologue for climate modeling and that embracing a variety of tools and methodologies is key to achieving convergent paths for meaningful progress. Where are we today? I'm going to be very brief. There's a lot of text, even though it's a short paper. I'm going to make it even briefer. In the mid-20th century, with the combined advances in computing and numerical modeling, the first general circulation models of the atmosphere came into being, led by Suki Manabe, who won the Nobel Prize. These models quickly advanced following two strands, one devoted to global weather predictions on short time scales and one devoted to simulation and predictions of the longer term climate. So Suki was the first one to run these coupled models with CO2 perturbations to argue what kind of warming we'll end up with, and he was basically right, even though he was, it was very early on with very low resolution and much more idealized components than today's very sophisticated models with much higher resolutions. The latter played an influential role in the 1960s in verifying that anthropogenic greenhouse gas emissions warm the climate, a development that would lead to Sukiro Manabe winning the Nobel Prize in Physics in 2021. These climate models have since solidified our theoretical understanding of global warming and have allowed us to understand the changes in the climate system as they have unfolded. Suki Manabe is still sitting and watching all these things. Climate models began with just the underlying physics of the atmosphere and ocean, but have since expanded massively in complexity to the Earth system models of today. We'll see a figure in a minute that not only simulate these Earth system models not only simulate the physical aspects of the climate system, but also biogeochemical and chemical aspects of the fully coupled atmosphere, ocean, land, sea ice, and land ice system. So carbon cycle as well. Projects such as the coupled model intercomparison CMIP under IPCC have allowed the global community to work together to address the question of what we should expect in terms of future climate change and to understand how our models behave. Furthermore, the use of simulations starting from different initial conditions but produced with a single climate model and identical external forcing has highlighted the importance of natural variability as a source of uncertainty in regional climate predictions across range of time scales. I hope you all know what natural variability means, what anthropogenic forcing means, and all that. If we don't know, don't panic. You can follow up on my other podcasts, much more detailed on climate modeling. Global ESMs, such as those used in CMIP or initial condition large ensembles, are an important source of understanding of the impacts of climate change and are one of the primary sources of information for stakeholders as to what the future might hold, either directly or by serving as the large-scale boundary conditions for various downscaling methodologies. The increasingly pressing need for climate information on a regional scale means that the demand for accurate information from climate models is now greater than ever before. The more the information you produce, more the forecasts you produce, more the demand and more the demand for better simulations and predictions. It has been argued that climate modeling is at so I jumped ahead. It's been argued that climate modeling is at a crossroads. Actually, I'm not showing figure 1, which is basically this is what did I do with the I screwed up, and yeah, this is just the history. So this is figure 2. That's anyway. let's not worry about it. This is just, we'll look at the history in a minute. It has been argued that climate modeling is at a crossroads and a step change is required to accelerate progress. Several different possible future divergent paths have been proposed for this step change, and each leverages a different tool. Here we reflect on the current state of climate modeling and discuss the different future paths, including their pros and cons. Simple models have some advantages, but they are not going to produce what we want. Complex models have some advantages, but they are going to be expensive to run, and so on. As a way to inform the future, we review the history of successful Earth system predictions across time scales. So we have weather, seasonal to interannual predictions, year-to-year predictions, and climate as long-term decadal time scales and longer, and highlight how multiple tools and steps were involved. We argue that the past is prologue for climate modeling, and embracing multiple futures is important as we work toward convergent paths for advances in climate modeling. While we do recognize that the translation of climate predictions into actionable and useful information requires attention to criteria such as the salience, so perceived relevance for a particular region, particular sector, and legitimacy, which is perceived objectivity, so that it's not being stated subjectively based on what you're trying to sell, and not just pure science of the model as it comes out. Other than just credibility and accuracy, that is the technical quality of the information, our focus here is on the latter. So technical quality of the information, credibility and accuracy, and the tools needed to produce such information. Okay, so let's look at the history, which is figure 1. So in the 1950s we just started with simple atmospheric models, and then by 1960s we were coupling land and atmosphere with multiple components like the ocean here and marine ecosystems. So let's just stick to the beginning here. Land came about, and then you started adding snow by the 1970s, vegetation and sea ice was added in the oceans. Marine ecosystems were added much later. Ice sheets were added even later, only recently. And you had in the meantime aerosols taking up more and more prominence. Carbon cycle, of course, because we were trying to do projections of the future on evolving carbon emissions and various options in terms of choices for humanity, and how that would produce emissions and what those emissions would mean for warming by 2100. And of course we realize upper atmosphere is very important, and not just the troposphere where weather is important, but in the longer term for climate change, the role of the upper atmosphere and the interactions between the lower atmosphere and the upper atmosphere were realized to be more and more important, and so on. So you can see how resolution began to improve. Going from there, it was like a blocks of land and ocean, whereas here you began to see shapes of continents and Greenland with ice and so on, and you had more detailed representation of the carbon chemistry to see radiation balance impacts, and that got even more sophisticated and complex and complicated. Started to do marine ecosystems as well, land ecosystems, mountains, land, ice, and so on, and you can now see the continents are much better, much more clearly represented, with many more features in the circulation, in the atmosphere, in the ocean, with eddies, and some are now even running at a resolution that are called hurricane permitting, which means they don't completely resolve hurricanes, but hurricanes are born and are seen to grow, so they can be used to understand hurricanes, and so on and so forth. Okay, so let's come back to here. What are the divergent paths? Kilometer scale models are one of them. In addition to providing more granular information that might be useful at this local scale, high resolution models might allow us to improve numerics and reduce the number of parameterizations needed. If you don't understand all this, then maybe you can skip it. But basically, when you have models, not everything is explicitly done with physics, in which case you are using data and some empirical relations to represent those processes, like let's say clouds. or aerosol impacts, then they are called parameterizations. At the kilometer scale, though, essential climate processes such as precipitating, deep convection, ocean mesoscale eddies, orography, land sea heterogeneity, and so on are more explicitly and arguably physically represented. This might also allow the focus to be diverted toward the other aspects of complexity which still require parameterization, such as cloud microphysics. You have to go from molecular level to planetary scales, or at least regional scales, ice sheets which can grow very large, and biochemical processes in the ocean and on land. High resolution alone, however, does not guarantee improved fidelity or fitness for climate simulations. In fact, long-standing large-scale biases still persist in kilometer-scale simulations. You can see the reference given there, but further understanding and refinements as we get used to working with these models will likely lead to further progress, much like what has occurred over the decades with lower resolution models. Additionally, the high computational costs of these kilometer scale models limit calibration or new developments of sub-grid scale processes and their parameterizations, and the creation of large ensembles for uncertainty quantification. If you don't understand this, basically models do amazing things. If you give it the energy coming from the sun, and they can produce the monsoon, the El Nino, and various other modes of variability, CO2 ecosystems, and feedbacks in the earth system, and so on, but they are imperfect. It's like a car that is working just fine, except it pulls a little to the right. So when we say improvements, calibrations, and so on, we are basically trying to make the models more perfect, reduce the pull, and so on and so forth. Ensembles are where you are making multiple simulations with a model, so that nature can go in many directions, even though we see only one direction it took from today to tomorrow, or from this season to the next. Potentially it could have taken many paths, and we try to capture those potential paths, because a model is not going to produce exactly the same path as nature, so you have to use the models to produce the potential paths Mother Nature could have taken. That's why we do ensembles. Okay, so physics augmented by parameter calibration, this is another approach that is being advocated. Parameter tuning or calibration of models continues to be central even at high resolution, and has seen a re-emergence with advanced techniques. Some of the most promising recent strategies include the systematic comparison of high resolution with single column simulations. Since you cannot run the global model, you can run a single column, then you can do many simulations and look for the model issues. And also, use of process-oriented metrics targeting processes believed to dominate the climate change response to anthropogenic forcing, and the use of nudged or initialized simulations. However, these techniques, while successful at tuning individual parameterizations or model components, still suffer from the curse of dimensionality in multi-scale and multi-physics systems, and compensate for model errors. In addition, transparent, rigorous, and reproducible practices are yet to emerge in this physics augmented by parameter calibration. Hydrophysics plus AI, hybrid physics plus AI, which I mentioned already. Despite the increased resolution and the improved understanding, many parameterizations are ad hoc, and tuning their free parameters might not be sufficient. So you get data, let's say on convection from the ocean or from land, from the tropics or mid-latitudes, and so on, and parameters based on those can be quite ad hoc. Not, you take data in one place, you produce a parameterization, and you put it into a global model, which obviously may not be applicable. So that's one example of what ad hoc means. AI approaches hold promise for rapid progress in discovering new data-driven parameterizations that will capture the complexity of multi-scale physics, significantly reducing computational cost. The potential drawbacks are that resulting parameterizations can lead to numerical instabilities through interactions with the resolved dynamics. So AI does some magic with the data and gives you something. Dynamics is trying to follow some first principles, and they may not match each other, and they might struggle to generalize to a new climate past or future, and might not be amenable to physical interpretation. In other words, they can be black box. There are interpretable and explainable models and so on that AIs are classified into. But without going into details, if you give it 50 years of data and 50 years of data has not seen a certain situation, then AI may not be able to capture it, whereas a dynamic model has in its first principles the potential for such unknown quantity that is there in data. Then emergent solutions can come out of physics models, but they may not come out of AI models in this case. Okay, so that's what we mean by struggle to generalize and not amenable to physical interpretation, or having struggles with the physics. In addition, this approach requires high quality data sets capable of capturing targeted subgrid fluxes that are to be parameterized. Basically, you have certain grid size that you are using to represent the sphere, atmosphere, ocean, land, ice, etc., and processes that happen less than that scale are not explicitly resolved by the model. So we call them subgrid scale processes, and we know they are important, so we try to represent them empirically, so that can be an issue as well. So here is just a schematic of convergent paths towards advances in climate modeling, embracing different approaches including hierarchical modeling, machine learning, and high resolution modeling will ultimately lead to improved climate projections. Hierarchical modeling is basically you are going to go from reductionist models to full models to very complete models with land ice and carbon cycle and ecosystems and so on. So you want improved projections, but also obviously many of us want improved predictions as well. So high resolution modeling is going in one direction, machine learning, conceptual modeling, but this mountain has to be climbed by different paths but head towards the same summit in terms of improving projections, which is the goal of this team that is writing it. But of course there are also people who want this to be done for climate prediction models. The issue is of course again the same. Can you ever get the climate simulation and climate predictions just at seasonal to intraannual time scales or decadal time scales to be accurate without worrying about the details of land use? How animals are changing land surface, how humans are changing land surface, how vegetation is responding, and so on and so forth. Okay, many of these things tend to be simplified in a climate prediction model, so that has to be a consideration as well for overall model improvement. Let's just close out by reading a few words on the future convergence and the path forward. A common theme that emerges from the above successes in predicting aspects of the Earth system is that multiple tools and approaches were involved, which we saw here. There were methodological advances such as improvements in observations, models, and assimilation methods. There were advances in fundamental understanding obtained through a hierarchy of approaches such as understanding of the basic ingredients required for El Nino Southern Oscillation prediction, and an understanding of the signals produced within the first climate projections, which lent credence to their validity. So all governments are beginning to at least participate in these negotiations based on the projections. Past is prologue, heeding these lessons and retaining and enhancing the wide variety of tools in our toolbox is a clear path toward improved understanding and prediction of climate change. Climate modeling has entered a critical era where regional signals have emerged from the noise and where accurate predictions of changes we will experience in the coming decade are more important than ever before. The growing climate change signal and lengthening observational record highlight areas where prior climate predictions have worked well, but they also uncover discrepancies that need to be resolved for both understanding and prediction. The escalating urgency with which society needs accurate climate information is leading to a variety of proposals for the future of climate modeling. That's what we saw here as well. They involve divergent paths and different tools, and in some cases involve a massive investment into one avenue, which understandably yields concerns that resources for other avenues may suffer, because it's a zero-sum game in terms of resources. However, none of the proposed approaches alone have yet proven sufficient for addressing the scientific challenges that the climate science community faces as of now. Indeed, I mean, they've been facing this for decades in terms of some of the chronic biases in the models. Indeed, these paths are also highly dependent on one another. For example, machine learning approaches require high-resolution model data for training, and with limited computational resources, high-resolution modeling efforts will almost certainly need to be augmented with emulators that can produce realistic probability distributions that account for both forced signals and internal variability. Furthermore, in order to have I chopped off something there, so let me correct that. Let me pause this for a minute. Okay, so let's read that again. I had chopped off something. So we were talking about future of modeling and convergence of all the different ideas being proposed, and we were here. For example, machine learning approaches require high-resolution model data for training, and with limited computational resources, high-resolution modeling efforts will almost certainly need to be augmented with emulators that produce realistic probability distributions that account for both forced signals and internal variability. These are technical terms. Basically, either you run a full model and do multiple ensembles, or you can have emulators that give you kind of the probability of things, probability distributions that account for forced signals, so anthropogenically induced greenhouse gas warming and those impacts, and then internal variability like El Nino and monsoon, which occur naturally. Furthermore, in order to have confidence in projections, using any modeling approach requires an underpinning of fundamental understanding of why such projected changes are being produced, which will almost certainly involve the use of hierarchical modeling approaches alongside basic theory. Okay, so that's a way to interpret future projections. You are giving them certain pathways, certain choices you make with energy and EVs and population and policies, and then you produce emissions, and then you give those emissions to models. Models take it forward, integrate, and produce climates, and those climates have extreme cyclones, changing, sea level rising, everything. Those need some interpretation, that need understanding the dynamics of why such a solution came out, as well as hierarchical modeling approaches. Indeed, we have learned something when models warmed too much, had bugs that were discovered or did not behave as expected. Finding the problems and figuring out the error is not a sign of failure, it's a sign of success and progress, because you can use the model biases and uncertainty to say they are useless, but actually they are very useful, because we know when they do something wrong, and that's very important, right? It's like a mechanic who knows why the car is not failing to start or move forward, or going in random directions, pulling and so on and so forth. Our view is that all approaches have a role to play, and that community needs to identify and understand the synergies between them to determine how best to maximize their benefits to address the problem of understanding unfolding climate change signals and providing actionable climate information for the coming decades. The past, and indeed many other areas of life, have taught us that collectively we are enriched by diversity. A wide range of approaches and tools alongside strategic methods that will allow them to inform one another to maximize their benefits will likely be the best, most rapid path towards advances in path toward advancing climate modeling. A large body of literature in the area of philosophy of science provides support to the benefits of approaches that leverage diverse and interdependent tools to build theoretically based and quantitative predictions of complex systems. Ambiguity, uncertainty, and etc. are part of complex systems. Last but not least, it's important to remember climate modeling involves the training of young scientists who benefit from diverse approaches, and we need to work together across generations to shape the direction of climate modeling. So this is a great advocacy piece in terms of allowing multiple paths to go forward, but focus towards the main goal. But as you can imagine what's happening now in the US with the funding cuts. I'm recording this in April 2025. I don't know, by the time I post it'll be a few months, because I have a lot of backlog. So you can see that it's not possible sometimes to support everything, even though they are important. So there may be some optimizing and cost benefit analysis needed, as well as to how to meet the goals for future projections. What time scale is very useful? Is it necessary to keep projecting to 2100? What are the uncertainties determined by 2100 as opposed to next couple of decades where real decisions are made, and so on and so forth. So let's leave it here.